Welcome to The Explainer. Today we're going to tackle one of those really intimidating topics in science, thermodynamics. But we're going to look at it from a completely different angle, one that changes it from this, dusty old theory about steam engines into something way more fundamental and honestly a lot more exciting.
So, let's just dive into this wild idea, one that was championed by thinkers like Claude Shannon and Edwin James. They basically asked, what if thermodynamics isn't really about heat at all? What if it's actually a universal theory of information, of probability? Really, it's about making the best possible guess when you just don't have all the facts.
So our story starts not in some fancy physics lab, but at a gambling table. And that's because the core principle behind all of thermodynamics, you could really understand it with a simple game of dice. At its heart, this is all about the science of just figuring things out with the information you have.
This, right here, is the absolute bedrock. It's the one single assumption you have to make. Whether you're talking about dice or atoms, you just start from this one place. Every possible outcome is equally likely, at least until you learn something new. It sounds almost too simple, right? But believe me, this one idea unlocks everything else.
You know, the funny thing is, the same exact logic that works for these two little dice, it also works for the trillions and trillions of atoms bouncing around in a bottle of gas. The only real difference is the scale, and it is a mind-boggling scale. With dice, we can count the outcomes, no problem. But with the gas, the number of possibilities is so ridiculously huge, we need a totally different way to think about it.
So why is rolling a 7 the most likely result? It's not some kind of magic. It's just, there are more ways for the dice to add up to 7 than any other number. That's it. It's more probable simply because more combinations make it happen. And that idea that things tend to happen because there are just more ways for them to happen, that is absolutely central to everything we're talking about today.
Okay, so how in the world do we deal with a number of possibilities that's so big it's basically uncountable? We need a special mathematical tool to get our heads around this astronomical number, a tool that was really perfected by information theory pioneers like Claude Shannon. First things first, we give this huge number a name. We call it multiplicity, and we use the Greek letter omega to represent it. So if we're rolling a 7 with our dice, the multiplicity is 6. Easy. But for that bottle of gas, omega is a number so gigantic it's completely meaningless to even try to write it down. So what do you do with a number that's impossibly big? You take its logarithm. This is the absolute genius move that tames infinity. It turns that monster number into a new, totally manageable quantity that we'll call S for uncertainty. Now, you've probably heard of S before, but by its more famous name, entropy. And just to give you a feel for the kind of scale we're talking about, this number on the screen, that's the multiplicity, the total number of possible ways the bits could be arranged, in just 32 megabytes of computer memory. It's a number that is way, way bigger than the number of atoms in the entire known universe. It's just completely beyond our comprehension.
And this is why logarithms are so incredibly useful. They take that insane, incomprehensible number and turn it into something simple we can all understand, 32 megabytes. Physicists do the exact same thing when they use entropy to talk about our uncertainty. It's all just a clever way to count things on a human-sized scale.
Okay, so now that we have this powerful idea of uncertainty, or entropy, we can actually use it to build a much deeper, more fundamental definition of something we all think we get, temperature. And it turns out it's not really about how hot or cold something feels.
So imagine you've got two systems, A and B. They're touching, so they can trade energy back and forth. They're naturally going to shuffle that energy around until they find the arrangement that has the highest possible total uncertainty, the state that can happen in the most possible ways. And that point of maximum probability, what we call equilibrium, that's where a very specific property of both systems becomes equal.
And that property is a slope. It measures how much a system's uncertainty, its entropy, goes up when you give it just a little bit of energy. Think of it like a measure of the system's thirst for energy. And that slope, that's the most fundamental definition of temperature there is. Two things are at the same temperature when their thirst for energy is exactly the same, so they just stop trading.
And this is where things get really, really cool. This whole thing isn't just some clever metaphor. No, this way of thinking is so fundamental that you can actually derive some of the biggest, most famous laws in all of physics just by counting possibilities.
Yeah, those laws you had to memorize in high school physics, like the ideal gas law, they just fall right out of the mathematics. They aren't some separate rules you have to learn. They're just the inevitable result of probability. Once you figure out how to count the states of a system, the laws just reveal themselves.
Even the legendary laws of thermodynamics start to make a lot more sense. The first law, that's just saying you can't create or destroy energy. And the second law, well, that's just the simple observation that systems will naturally drift toward the states that are overwhelmingly more probable, the states with higher uncertainty or entropy. Your room doesn't get messy because of some mysterious cosmic force. It gets messy because there are a gazillion more ways for it to be messy than for it to be tidy.
And that makes these laws an incredibly powerful, let's call it a BS detector. They tell us what is fundamentally possible and what just isn't. No matter how clever you are, you cannot build a perpetual motion machine because it violates these basic rules of probability. It's not a technology problem we haven't solved yet. It's a statistical impossibility. Period.
Now, let's just see how far we can push this idea, because it goes way, way beyond gases in a bottle. This way of thinking applies to the logic gates in your computer, the genetic code of life, and even the very nature of what it means to know something.
Okay, let's go back to our information analogy for a second. Let's say you have two totally separate random documents. Your total uncertainty about what's in both of them is just your uncertainty about A plus your uncertainty about B. Makes sense, right?
But what if I give you one more tiny piece of information? What if I tell you that document B is a perfect, exact copy of document A? All of a sudden, your uncertainty just collapses. The moment you know what's in A, you instantly know everything about B. They aren't independent anymore. They're correlated.
That reduction in uncertainty, we call that mutual information. And here's the kicker, the physical cost. Creating that information, that correlation, whether you're photocopying a document or your cells are transcribing DNA, that is not free. The laws of thermodynamics say that creating knowledge in one place means you have to spend energy and create waste heat somewhere else.
And this is where it gets really profound. What is life? Well, from this perspective, life is a machine that creates mutual information. DNA is a physical code that stores information about the environment. It's a record of what works. And our ideas? From the first alphabets to the global internet, they're just another kind of code that replicates itself. It points to this deep, symbiotic dance between living things and the information they carry.
So, the grand takeaway here is that thermodynamics isn't just about heat engines. It's the fundamental logic for how to reason about any system. Physical, biological, you name it, where you don't have all the facts. It's the universal rulebook for a universe that plays by the laws of probability.
Which really just leaves us with one last big question to chew on. If life is an engine for storing information, and if our ideas are these evolving codes, if the universe is constantly building this record of itself, then what's the story that's being written? And maybe more importantly, what's our part in writing it?